Picture yourself embarking on the most extraordinary mountaineering expedition ever attempted. You're not on Earth anymore. You're standing at the base of a towering peak on Titan, Saturn's largest moon. This is unlike any climbing experience in human history. Above you, clouds of methane drift lazily in the thick, orange-tinted atmosphere, occasionally releasing drops of liquid methane rain that fall in slow motion through the weak gravity, creating alien rivers that carve through the icy landscape. The ground beneath your feet isn't made of familiar granite or limestone. It's water ice frozen so hard it behaves like solid rock. Each step you take feels surreal, almost dreamlike, as Titan's gravity, just 1/7 of Earth's, makes you feel almost weightless. Your movements are graceful but strange, like an astronaut dancing on the moon. Except here, you're surrounded by a dense atmosphere that gives you resistance, making every motion feel like you're moving through invisible honey. Welcome to Titan, Saturn's enigmatic moon, where everything we thought we knew about geology is turned on its head. This is a world where mountains are made of ice harder than concrete, where rivers flow with liquid hydrocarbons instead of water, and where the atmospheric pressure is 50% higher than Earth's at sea level. Here, the mountains stand as frozen sentinels, their formation and existence challenging our fundamental understanding of planetary geology. Today, we're going to venture deep into the mysteries of Titan's mountainous terrain, comparing these alien peaks to their earthly counterparts. We'll discover how these ice mountains form in conditions so cold that water ice behaves like rock, where methane takes on the role that water plays on Earth, and where geological processes familiar to us operate in slow motion under alien conditions. This journey will fundamentally change how you think about mountain formation, geological processes, and the incredible diversity of landscapes that can exist in our solar system. Before we begin this fascinating exploration of Titan's geological wonders, make sure you're part of our cosmic community here at Exploring the Universe. Hit that subscribe button and turn on notifications to join us on our weekly journeys through the most fascinating corners of our solar system. From the methane seas of Titan to the volcanic plains of Io, we're here to bring the wonders of space right to your screen. Let's embark together on this extraordinary voyage to understand one of the most intriguing worlds in our cosmic neighborhood. Among all the moons in our vast solar system, Titan stands as a remarkable anomaly, a world that tantalizes scientists with its Earth-like features while remaining fundamentally alien. As Saturn's largest satellite, this celestial body commands attention not just for its impressive size, larger than the planet Mercury, but for being the only moon in our solar system cloaked in a thick, substantial atmosphere. This atmosphere, primarily composed of nitrogen, creates a mysterious orange haze that shrouds the moon's surface, making Titan appear as a glowing orange orb when viewed from space. But what makes this atmosphere truly extraordinary is its density. It's about 4 times thicker than Earth's atmosphere at sea level. This means that if you were standing on Titan's surface, the air pressure would feel similar to what a diver experiences about 15 feet underwater on Earth. The temperature regime on Titan is almost beyond human comprehension. At an average of 179 degrees Celsius, this is a world locked in a perpetual deep freeze. At these temperatures, water ice becomes as hard as terrestrial rock, and methane, a gas on Earth, exists in all 3 states, as a gas in the atmosphere, as a liquid in lakes and seas, and as a solid in the form of frost and possibly even methane snow. Perhaps the most captivating aspect of Titan's landscape is its Earth-like hydrological cycle, but with a crucial difference. Instead of water, liquid methane falls as rain from the orange skies, collecting in vast lakes and seas that dot the moon's polar regions. The largest of these liquid bodies, Kraken Mare, is larger than Earth's Caspian Sea, spanning an area of approximately 400,000 square kilometers. These dark, smooth surfaces reflect the dim sunlight that manages to penetrate Titan's thick atmosphere, creating a ghostly shimmer across the hydrocarbon seas. To truly appreciate Titan's uniqueness, consider this analogy. If Earth is our cozy family home, maintained at a comfortable room temperature with familiar water-based weather patterns, then Titan is like that same home transported into a cosmic deep freezer. The basic architectural elements remain: mountains, valleys, lakes, and rain, but everything operates in slow motion under drastically different conditions. The rivers still flow, but they're filled with liquid methane at temperatures cold enough to instantly freeze human blood. The waves still crash on alien shores, but they move through a thick atmosphere in reduced gravity, creating patterns that would appear bizarrely slow to human eyes. This frozen version of Earth presents us with an extraordinary natural laboratory. Here, we can observe familiar geological and meteorological processes playing out under radically different conditions, giving us unprecedented insights into how climate systems and geological processes might operate on other worlds. The presence of organic compounds and complex chemical processes on Titan also makes it a crucial target in our search for understanding the potential for life in the universe, even if that life might take forms radically different from what we know on Earth. Just as our understanding of Earth's geology revolutionized our perception of our home planet, studying Titan's unique features is reshaping our comprehension of what's possible in planetary science. This frozen world, with its thick atmosphere and Earth-like processes, stands as a testament to the incredible diversity of worlds that exist in our cosmic neighborhood, challenging our assumptions about what constitutes a potentially habitable world. When we think of mountains on Earth, we envision massive formations of granite and basalt, thrust upward by tectonic forces over millions of years. But on Titan, we need to completely reimagine our understanding of what makes a mountain. Here, at temperatures hovering around 179°C, water ice becomes the primary building material of these alien peaks, creating mountains that are essentially colossal frozen structures unlike anything we've seen on Earth. To truly appreciate the unique nature of Titan's mountains, let's delve into their composition. On Earth, our mountains are primarily composed of igneous rocks like granite and metamorphic rocks like schist and gneiss, materials formed under intense heat and pressure. These rocks are incredibly dense and robust, capable of supporting immense weights and resisting erosion over millions of years. In contrast, Titan's mountains are primarily composed of water ice, but not the kind of ice we're familiar with in our freezers. The ice that forms Titan's mountains exists in a special crystalline form known as ice. At Titan's extremely low temperatures, this ice becomes remarkably rigid and strong. The bonds between water molecules become so tight and organized that the ice behaves more like Earth's bedrock than the fragile ice we know. This is a crucial point that often surprises people. At these temperatures, water ice is not brittle or easily broken. It's as hard as granite on Earth. Think of it this way. If you could magically transport a piece of Titan's ice mountain to Earth, it wouldn't simply melt away like a regular ice cube. Instead, it would initially maintain its rock-like properties until our warmer temperatures began to affect its crystalline structure. This is because the ice on Titan exists in a state where the molecular bonds are so strong that they create a material with properties more similar to terrestrial rock than to what we typically think of as ice. The structural integrity of these ice mountains is further enhanced by the presence of other compounds. Mixed within the water ice are various hydrocarbon compounds and other frozen volatiles that act like nature's cement, creating an even more robust building material. This mixture of materials, combined with Titan's lower gravity, about 1/7 of Earth's, allows these ice mountains to reach impressive heights while maintaining their structural stability. One of the most fascinating aspects of these formations is how they interact with Titan's methane cycle. Just as Earth's mountains are shaped by water erosion, Titan's ice mountains are sculpted by liquid methane. The methane rain and rivers carve channels and valleys into these ice formations, creating landscapes that look remarkably similar to Earth's mountain ranges, despite being composed of entirely different materials. When we compare the density and hardness of Earth's rocky mountains to Titan's ice mountains, we find something remarkable. At Titan's temperatures, the ice mountains have a compressive strength comparable to many terrestrial rocks. This means that while they're made of what we would consider an exotic building material, they're capable of supporting their own weight and maintaining their shape just as effectively as Earth's mountains do under our planet's conditions. The presence of these ice mountains on Titan also tells us something profound about the Moon's geological history. Their very existence suggests that Titan has experienced significant geological activity throughout its history, possibly including cryovolcanism, ice volcanism, and tectonic processes that have helped shape and maintain these frozen peaks over millions or billions of years. Understanding these ice mountains and their composition isn't just an academic exercise, it's crucial for planning future missions to Titan. Any lander or rover we send to explore these formations will need to be designed with their unique properties in mind, capable of navigating and analyzing terrain that behaves like rock but is fundamentally different from anything we've explored on other worlds. The formation of mountains on Titan represents one of the most fascinating examples of how familiar geological processes can operate under alien conditions. The primary mechanisms that build these icy peaks involve two main processes, ice tectonics and cryovolcanism, both of which operate in ways that both mirror and diverge from their Earth counterparts in remarkable ways. Ice tectonics on Titan operates similarly to plate tectonics on Earth, but with a crucial difference. Instead of moving crustal plates made of rock, Titan's surface moves massive sheets of ice. Imagine Titan's outer shell as a giant jigsaw puzzle made of ice, floating on a subsurface ocean of liquid water and ammonia. As these ice sheets move, they create tremendous forces that can cause buckling, folding and thrust faulting, pushing massive blocks of ice upward to form mountain ranges. The process is remarkably similar to how the Himalayas formed on Earth, but instead of continental plates colliding to thrust up rocky peaks, we have enormous ice sheets converging to create mountains of frozen water. The lower gravity on Titan actually allows these ice mountains to grow quite tall, despite being made of what we would consider a weaker material on Earth. Cryovolcanism adds another fascinating dimension to Titan's mountain-building processes. Unlike Earth's volcanoes that spew molten rock, Titan's cryovolcanoes erupt with a mixture of water, ammonia, and other compounds that are liquid at the higher temperatures of the Moon's interior. When this mixture reaches the frigid surface, it freezes almost instantly, building up layers of new material that can form dome-like mountains and ridge systems. Think of this process like making a reverse ice cream cone. Instead of warm material melting cold material, we have relatively warm, but still quite cold by Earth standards, liquid water mixtures freezing solid as they emerge onto the even colder surface. Over time, repeated cryovolcanic eruptions can build up substantial formations that contribute to Titan's unique topography. Here's where our hot chocolate analogy becomes particularly illuminating. When you leave a cup of hot chocolate to cool, you might notice a pattern of cracks forming on the surface as it solidifies. These cracks form because the cooling liquid contracts and creates stress patterns in the solidifying surface. On Titan, similar processes occur on a massive scale when layers of water-rich materials freeze and contract, creating systems of cracks and ridges that can develop into mountain-like features. But there's more to the story. The presence of organic compounds in Titan's crust adds another layer of complexity to these formation processes. These materials can act as a kind of cement, helping to stabilize the ice structures and contributing to their long-term stability. The interaction between these organic compounds and the water ice creates unique structural properties that we're still working to fully understand. Before we continue our exploration of Titan's fascinating geology, we'd love to hear from you. In the comments below, share with us. If you were planning an expedition to climb one of Titan's icy peaks, what special equipment would you bring along? Remember, you'll be dealing with temperatures of 179 degrees Celsius, a thick atmosphere, and surfaces made of rock-hard ice. Would you design special crampons for the ice rock surface? What kind of thermal protection would your suit need? How would you handle the methane rain? The most creative and scientifically sound answers will be featured in our next video about Titan's methane lakes and seas. Think about the unique challenges. Equipment that works perfectly on Earth might behave very differently in Titan's extreme cold and different gravitational field. Your thermal protection would need to handle not just the cold, but also prevent any condensation of methane on your equipment. Share your ideas, and let's imagine together what it would take to explore these extraordinary mountains. The mountains of Titan present us with a fascinating set of characteristics that make them unique in our solar system. Their formation, structure, and evolution are governed by a complex interplay of factors that create landscapes both eerily familiar and profoundly alien. One of the most intriguing aspects of Titan's mountains is their height limitation. Unlike Earth's mountains, which can reach heights of over 8 kilometers, Titan's peaks are constrained by the mechanical properties of their icy composition. The water ice that forms these mountains, despite being hard as rock at Titan's temperatures, still has fundamental structural limits. When we combine this with Titan's lower gravity, about 1/7 of Earth's, we get mountains that typically reach heights of 1 to 2 kilometers, with some exceptional peaks reaching up to 3 kilometers. This height limitation creates a remarkable equivalency. A 3-kilometer mountain on Titan would present a climbing challenge comparable to scaling Mount Everest on Earth. This isn't just because of the physical height, but because of the combination of factors at play. The lower gravity means less compression of the ice at the mountain's base, allowing for steeper slopes than would be possible with similar materials on Earth. Additionally, the denser atmosphere creates wind patterns and erosion effects that shape these mountains in unique ways, making them formidable challenges for any future exploration. The erosion processes on Titan are particularly fascinating. While Earth's mountains are carved by water and wind, Titan's peaks are sculpted by flowing liquid methane. This creates erosion patterns that mirror Earth's water-carved valleys and canyons, but with crucial differences. The liquid methane, being less dense than water and flowing under lower gravity, creates wider valleys and more gradual slopes. The extreme cold also means that erosion happens more slowly than on Earth, but the processes are continuous thanks to Titan's active methane cycle. Around these icy mountains, Titan presents another remarkable feature: vast fields of hydrocarbon dunes. These dunes, some reaching heights of up to 100 meters, are composed of small particles of organic compounds, essentially frozen atmospheric smog that has settled to the surface. They create a landscape that looks surprisingly similar to Earth's great deserts, but instead of silica sand, these dunes are made of organic materials that would be gases or liquids on Earth. The interaction between these dunes and the mountains creates unique geological features. The dunes often wrap around the bases of mountains, creating patterns that help scientists understand Titan's wind regimes. In some areas, the dunes appear to climb partway up mountain slopes, creating a striking visual contrast between the dark organic materials and the lighter ice rock mountains. Another unique characteristic is how these mountains weather over time. The combination of methane rain, extreme cold, and organic chemistry creates weathering patterns unlike anything seen on Earth. The methane rain doesn't just erode the mountains, It can dissolve certain components of the ice mixture, potentially creating cave systems and complex internal structures within the mountains themselves. The mountains also play a crucial role in Titan's methane cycle. Just as Earth's mountains influence our weather patterns by forcing air masses upward and creating precipitation, Titan's peaks affect the movement of methane-laden air masses. This creates localized weather patterns that can include methane rain shadows on the leeward sides of mountains, just as we see rain shadows on Earth. The structural composition of these mountains reveals another fascinating aspect. They likely contain layers of different types of ice and frozen organic compounds. This layering, visible in some radar images from the Cassini mission, suggests that these mountains have complex histories, possibly including periods of cryovolcanic activity interspersed with periods of atmospheric deposition of organic materials. The relationship between Titan's mountains and its subsurface ocean adds another layer of intrigue. Evidence suggests that some of these mountains might be connected to the Moon's internal liquid water ocean through complex systems of cracks and faults. This raises the possibility that materials from the subsurface ocean might occasionally make their way to the surface through these mountain systems, potentially bringing with them chemicals relevant to the search for life. The Cassini-Huygens mission revolutionized our understanding of Titan's geology, particularly through its groundbreaking radar observations that penetrated the Moon's thick orange haze. Over its 13-year mission surveying the Saturnian system, Cassini's radar instrument mapped approximately 40% of Titan's surface, revealing a world far more complex and Earth-like than anyone had imagined. One of Cassini's most significant discoveries was the identification of extensive mountain chains across Titan's surface. The spacecraft's radar system revealed three major mountainous regions: the Mithrim Montes, Xanadu, and the Equatorial Ridge System. The Mithrim Montes proved particularly fascinating, with peaks reaching heights of up to 3,237 meters, the highest elevation ever measured on Titan. These mountains, composed primarily of water ice as hard as rock, demonstrated that Titan's geological processes could create formations rivaling some of Earth's most impressive mountain ranges. The radar data also unveiled unexpected patterns in mountain distribution. Unlike Earth, where mountain ranges often form in long, continuous chains due to plate tectonics, Titan's mountains frequently appear in more isolated clusters or shorter chains. This distribution pattern has helped scientists understand the unique ice tectonic processes shaping Titan's surface. Among Cassini's most spectacular findings were the images of Titan's equatorial region, where mountains meet vast fields of organic dunes. The radar imagery showed how these mountains interact with Titan's weather systems, creating wind patterns that shape the surrounding dune fields. These images revealed a dynamic world where solid ice, liquid methane, and organic particles interact in ways that mirror Earth's geological processes while remaining distinctly alien. The mission also made a crucial discovery about mountain formation on Titan through its gravity measurements. These data suggested that Titan's icy crust might be more rigid than previously thought, allowing for the formation and maintenance of substantial mountain ranges despite being composed primarily of water ice. This finding challenged our previous understanding of how ice behaves at such extreme temperatures. One of the most intriguing aspects of Cassini's mountain observations was the detection of what appeared to be recent geological activity. Fresh-looking scarps and ridges suggested that some of Titan's mountains might be relatively young in geological terms, indicating that the Moon remains geologically active. This activity might be driven by tidal forces from Saturn or by internal processes related to Titan's subsurface ocean. Looking toward the future, NASA's Dragonfly mission, scheduled to launch in 2027 and arrive at Titan in 2034, promises to revolutionize our understanding of these formations even further. This innovative rotorcraft will be able to fly through Titan's thick atmosphere, capturing unprecedented close-up images of mountain faces, valleys, and ridges. Its ability to move between different sites will allow it to examine various geological features from multiple angles and altitudes, providing us with detailed data about mountain composition, structure, and formation processes. Dragonfly's advanced imaging systems and scientific instruments will be able to analyze the chemical composition of mountain materials directly, potentially revealing how these formations were created and how they've changed over time. The mission could also help us understand the role of organic materials in mountain formation and evolution, as well as the potential for these geological features to harbor prebiotic chemistry. The mission will build upon Cassini's discoveries by providing ground truth data that can help calibrate and interpret the radar images we already have. This will be particularly valuable for understanding features that appeared ambiguous in Cassini's radar data, such as possible cryovolcanic features and complex erosional patterns. Moreover, Dragonfly's ability to sample materials directly from different geological formations could help resolve ongoing debates about the exact composition of Titan's mountains and how they maintain their structure in Titan's unique environment. This mission represents our next great leap in understanding Titan's fascinating geology, promising to reveal details about these alien mountains that we can only speculate about based on Cassini's data. The study of Titan's mountains has revolutionized our understanding of planetary geology and opened new avenues in our search for life beyond Earth. These frozen formations serve as a geological record book, telling a complex story about Titan's past and offering insights into both our own planet's history and the potential for life in the cosmos. From a geological perspective, Titan's mountains provide crucial evidence about the Moon's evolution over billions of years. The very existence of these ice rock formations tells us that Titan has experienced significant geological activity throughout its history. The distribution and structure of these mountains suggest that Titan, like Earth, has undergone periods of intense geological transformation. The presence of tectonic features in the ice crust indicates that Titan has experienced forces similar to those that shaped Earth's continents, albeit under radically different conditions. These mountains also provide evidence of Titan's internal structure. Their formation and maintenance require a rigid, icy crust of significant thickness, while their ongoing evolution suggests the presence of a subsurface ocean. This combination of rigid surface and liquid interior tells us that Titan has maintained internal heat over billions of years, likely through a combination of radioactive decay and tidal heating from Saturn's gravitational pull. The implications for astrobiology are particularly exciting. The interaction between Titan's water-ice mountains and its methane-based weather system creates environments where complex organic chemistry can occur. The mountain's surfaces and internal structures might provide protected spaces where organic compounds can concentrate and interact over long periods. The presence of liquid methane flowing through these formations creates potential habitats that, while extreme by Earth standards, could theoretically support forms of life fundamentally different from those we know. The mountain's role in Titan's methane cycle is especially significant for astrobiology. Just as Earth's mountains influence the water cycle and create diverse microclimates that support various forms of life, Titan's peaks create local conditions that could concentrate organic compounds and provide energy gradients necessary for potential biological processes. The discovery of organic-rich deposits around these mountains suggests they play a crucial role in Titan's complex organic chemistry. Perhaps most intriguingly, Titan's mountains offer us a window into what Earth might have looked like in its early history. The complex interaction between organic compounds and geological processes on Titan may mirror conditions on early Earth before the rise of oxygen-producing life. The presence of complex organic chemistry in a water-ice environment provides a natural laboratory for studying how prebiotic chemistry might have operated on our own planet billions of years ago. This connection to early Earth extends beyond just chemistry. The way Titan's mountains interact with its atmosphere and liquid cycles provides insights into how geological processes might operate on other worlds with different chemical compositions. This helps us understand how fundamental geological processes can adapt to different planetary conditions, expanding our understanding of what's possible in planetary evolution. Furthermore, studying these mountains has forced scientists to reconsider what constitutes geological activity. The discovery that water ice can behave like rock and support mountain-sized formations has expanded our definition of geological processes and materials. This broader understanding is crucial as we explore other worlds in our solar system and beyond, helping us recognize and interpret geological features that might form under conditions very different from those on Earth. The mountains of Titan also play a crucial role in our understanding of climate systems on other worlds. Their interaction with Titan's thick atmosphere and methane cycle provides a second example, after Earth, of how geological features can influence planetary weather patterns. This helps us develop more comprehensive models of how climate systems might operate on other planets and moons throughout the universe. As we continue to study these fascinating formations, they challenge us to expand our thinking about what's possible in planetary science. They remind us that nature can create familiar-looking features using very different materials and processes than those we know on Earth. This understanding is crucial as we explore other worlds and search for life in the universe, helping us avoid Earth-centric assumptions about how geological processes must operate or what conditions are necessary for life to emerge. The ongoing study of Titan's mountains continues to yield new insights, pushing the boundaries of our understanding in planetary science, astrobiology, and the search for life beyond Earth. As we prepare for future missions like Dragonfly, these frozen peaks stand as testament to the incredible diversity of geological processes in our solar system and their potential role in the origin and evolution of life. As we conclude our journey through the extraordinary mountain ranges of Titan, we find ourselves standing at the intersection of familiarity and alienness. These towering formations of ice rock, sculpted by methane rain and crowned by orange skies, represent far more than mere geological curiosities. They are silent sentinels that hold within their frozen layers stories of planetary evolution, potential for life, and clues to our own world's distant past. The mountains of Titan challenge our understanding of what's possible in planetary geology. In their unique composition, we see how nature can create familiar landscapes using entirely different materials and processes. These peaks, standing firm in temperatures cold enough to freeze water into stone-like hardness, remind us that the universe's creativity far exceeds our earthbound expectations. Through studying these formations, we've gained unprecedented insights into how geological processes can operate under radically different conditions. The interaction between Titan's mountains and its methane cycle mirrors Earth's water cycle in fascinating ways, while the presence of organic compounds in these structures opens new possibilities in our search for life beyond Earth. These ice mountains also serve as time capsules, preserving evidence of Titan's geological history and ongoing processes. They tell us stories of cryovolcanic eruptions, tectonic movements in ice sheets, and the constant interplay between surface and atmosphere that makes Titan one of the most Earth-like worlds in our solar system, despite its profound differences. Perhaps most importantly, Titan's mountains remind us that we live in a universe of endless surprises. Just when we think we understand how planetary geology works, we discover a world where mountains of ice stand as tall as Earth's peaks, where methane rain carves valleys through frozen water, and where familiar processes operate under unfamiliar rules. If you've enjoyed today's journey through Titan's mountainous terrain, please share this video with fellow space enthusiasts who might appreciate these geological wonders. Hit the subscribe button and join our growing community of cosmic explorers here at Exploring the Universe. Together, we'll continue to unravel the mysteries of our solar system's most intriguing worlds. Remember to ring that notification bell to ensure you don't miss next week's deep dive into Titan's liquid methane seas. Your comments and questions about today's episode have been fantastic, and we look forward to continuing these fascinating discussions about one of the solar system's most extraordinary moons. Until next time, keep looking up and wondering about the incredible diversity of worlds that await our exploration. This is Exploring the Universe, where every week we bring the cosmos a little closer to home.